Good afternoon. Again, good afternoon.
Good afternoon.
Got to get myself into the swing of how this class works. I'm a psychologist. I'm in particular a cognitive developmental psychologist. I study how thinking processes change with development. You see what we're going to cover over the next two class periods on Wednesday. So let me start by talking, actually before I talk about development, I see some people taking notes by hand and some people taking notes by computer. One of the things cognitive developmental psychologists do, or cognitive psychologists in general, we look at things that facilitate or interfere with learning. Contrary to popular belief, people who take notes by computer don't do as well on exams as people who take notes by hand. We understand that by looking at the kinds of notes people take. When people take notes by computer, because they can do it really rapidly, they are more likely to write down verbatim what the instructor is saying. So people who take notes by computer take more notes, but they don't process it into their own thoughts. One of the things that I'll be pushing both today and next Wednesday is that thinking is a constructive process. If you try and learn things passively by just having them wash over you, you're very unlikely to learn them, and if you do learn them, you're likely to have trouble remembering them. So we will be bumping into a bunch of things that show being more actively engaged in the content as you learn makes you retain the information better. So for those of you who like to take notes by computer, what I recommend is you think about what we've learned from the research we've done and don't write things down verbatim. Try and recode them into your own language and you will remember them better. So let me begin by talking a little bit about development. Those of us who study development think of it as involving a kind of predictable change over time. There's a timeline. Some people are a little faster on that timeline, some people are a little slower, but human beings change in predictable ways. There are both quantitative and qualitative changes. So for example, if you think of a characteristic of young babies, they have a certain height. Over time, they get taller. But that's a quantitative change. It's just a gradual increase in height until somewhere between 14 and about 20 years of age, depending on whether it's a male or a female, fast or slow developer. Then you are at your maximum height until you get to be my age, and then height starts to go down again as the spaces between vertebrae collapse and so on. So that's a quantitative change. There also is qualitative change. So for example, in characterizing how individuals think at different ages, very young babies think about the here and now. They are aware of and can think about things that are right in front of them, but they don't have a symbolic system for representing those things when they are absent. So with respect to objects, they're very interested in them when they're right in front of them, but if you put an object under a towel or something in front of them, they behave as if that object ceases to exist. They don't represent the idea of the object when it's absent. By about a year and a half, they can represent objects just fine, but symbolic representation brings with it challenges. If all you do is pay attention to what's happening now, you don't have to learn a rule about gravity. You don't have to know that when you drop things, they fall, because all you're aware of are things as they happen. Every time you drop it, it falls. You don't have to remember that the physical world imposes that constraint. As you get the ability to symbolically represent things, now you have to learn about the constraints on those things. And that kind of learning happens starting around 1.5 years of age, and up until 7 years of age or thereabouts, it has lots and lots of errors in reasoning about physical causality and other things in the absence of actually experiencing something. But by the time kids are entering school, they are very good at reasoning about concrete things. So you can teach them addition and subtraction to help them understand how if you take something that's 2 feet long and something that's 3 feet long, you put it together, you got something 5 feet long. Okay? Nice, concrete features of the world. But they don't reason well about abstract features of the world. So for example, although they reason about length just fine, they make errors in reasoning about density. So if you ask a typical 8-year-old, why does something float when you put it in water? They will tell you it's because it's light. Why does it sink when you put it in water? That's because it's heavy. And you say, well then why does a battleship float? It's obviously big and heavy and made out of metal, yet you can only understand how buoyancy works if you can make use of the concept of density. So that's kind of systematic change that happens with development. And an important feature, I mentioned it before, is that this is a constructive process. So kids construct ideas as they're developing thinking that are not like any idea anybody around them is expressing. They are constructing their best understanding of the world, and it progressively gets better and better until you get into adolescence. So even before you got to college, at the level of how your reasoning system works, you've got it as good as it gets. Okay? You will learn more strategies for solving problems and so on, but you won't develop more underlying conceptual skills beyond what you have now. But your task now is to exercise those skills that you have. A final piece here is the notion that development is a product of an interaction between what you're given genetically and the experiences you have in the world. Neither one determines how you will develop. It's the two together, and we'll encounter a number of things like that. But given that you've just talked about the nervous system, I want to do a little illustration of the difference between the way very young babies crawl and the way older babies crawl. Not every baby learns to crawl before it walks, but they learn some kind of mechanism for getting around before they start to walk. So, first, the young babies. Now, from what you learned about the nervous system, do you have any idea why that would change between young babies and older babies? How do the neurons mature after babies are born? Yes? Yeah, there are two major things that go on in it. One is they make new connections, and the other is that myelinization, that fatty tissue on the neuron, is an important part of brain development in the first few years of life. And in fact, the connections between the two hemispheres aren't myelinated when babies are born. So babies are functioning as split brain organism. This side of the brain controlling this side of the body, this side of the brain controlling this side of the body, but very poor communication between them. If you don't have communication between them, then you can't coordinate moving a limb on one side of the body with moving a limb on the other side of the body. So the nature of the nervous system and how it develops provides constraints on the behaviors and later the thoughts that kids will have as they develop. As an analogy, if you've ever watched a giraffe walk, giraffes have a really awkward walk. On. Where is their brain? Way up there. They're very tall. To move a limb, you have to send a signal from the brain all the way down to the muscles that control the legs. Neural signals travel over time, okay? They have a longer neural pathway than most organisms, and therefore it's very hard to coordinate walking for a giraffe the way you might coordinate walking for a horse, or a dog, or a cat. Okay? Here's a model, sometimes called the modal model, of our cognitive system. The notion is we do a bunch of things. We take information in from the environment. We have sense organs that do that, our eyes, our ears, our sense of touch, our sense of smell. So information comes in through perceptual systems. It is processed or understood in some way, and that may lead to an action, or it may lead to simply storage and memory, so information gets stored for later thinking and action. So it's worth thinking about that flow of information. Some things that we learn, we have explicit memory about. We can talk about it. Some things that we learn, we don't really know, we never have stopped to think about exactly how we do it. So I'm going to do another illustration here that doesn't involve me crawling across the stage. I want all of you to simulate changing lanes on the freeway. So I'm going to tell you the part you don't have to simulate. Imagine you're driving down the freeway. You're in the slow lane. Okay? You're going to change into the next lane over. And let's presume you have done all the following things. You have turned on your turn indicator, you have checked your mirror, you've looked in your blind spot to make sure there's not a car where you can't see. So now, what I want each of you to do, put your hands out in front of you as if you had two hands on the steering wheel. I want you now to do what you would do with your hands to change lanes and then continue down the freeway. So folks, notice what you do and notice what so you're driving along, and now I'm going to change lanes. Okay? Yeah, and everybody do it again. Some of you did it really fast, and I think you spun out. Do it slowly. Okay? So now let's talk about what you did. What I saw people doing, I'll do it up here. I'm driving down the freeway, now I'm going to change the lane over here. What I saw people do is this. Is that correct?
Yeah.
Okay, well let's think about what happens. Turn the wheel like this. That angles my car this way. I then bring my hand back like this. I'm now pointed in this direction. Continue that way. I run into the center divider. What you actually do when you change lanes is you turn the wheel like this. That changes the angle of the car. When you get to the next lane, you then turn the wheel the other way to straighten yourself out. Now, how many people drove to campus today? How many of you ran into the center barrier. Okay? That's good. So notice, you know how to drive, but you don't know what you do when you drive. And the illustration of what you did when I asked you to do that, same issue happens when you ask somebody how they change, how do you turn a bicycle? So imagine I'm riding along on my bicycle. I want to go that way. If you do that, you fall over. The reason is you have to have the center of gravity under that forest line. So you first, to go that way, turn your handlebars a little bit this way. You don't move out from under you. Now you can turn back the other way and turn the bicycle. 4-year-olds learn how to do this, but they don't know what they do when they do it. Okay? So when we look at how people process things cognitively, their idea about how they do it may be different than how they do it. Okay? So there's a concept, it's really a concept out of philosophy called naive realism. It's the belief that what you see in the world, that is your perceptual understanding of the world, is in fact an accurate reflection of what's out there in the world. Most people wander around in the world with an underlying belief in naive realism. But we know there's lots of information out there. So for example, for sound, human beings are limited to hearing sounds in the range about 20 cycles per second, that is 20 vibrations per second, that's a low-pitched sound, to about 20,000 cycles per second. So when you blow a dog whistle, you don't hear it. But dogs hear it because they're pitched at about 40, the dog whistles are pitched at about 40,000 hertz, and that's within the hearing range of the dog. So dogs hear things we don't hear. Okay. Another example, in the visual range, we are limited to a range in the light spectrum that is narrower than some other animals. Butterflies see other butterflies differently than we do because they can perceive much shorter wavelength light. Okay, I could give other examples, but I'll stop there and talk about another phenomenon. Imagine I have in front of me here 3 buckets. This one is full of ice water. This one is full of hot water. And the one in the middle is full of lukewarm water. And I put one hand in the ice water and the other hand in the hot water. Is everybody with me thus far?
Yeah.
Okay. After I leave them there for about 30 seconds, I then put both hands in the lukewarm water that's in the middle. You get a very strange sensation because there your hands are in the same bucket of water. This hand feels like it's in cold water, and this hand feels like it's in hot water. It's a temperature illusion. The way we perceive temperature is in fact influenced by the past temperatures that we've just been experiencing. So that's a temperature illusion. The moon illusion. How many of you have ever seen a full moon rising? I really regret that the rest of you haven't. A full moon rising is a very beautiful thing. When you look at the full moon as it rises, right at the horizon, the moon looks big. When you look at the full moon at midnight, directly overhead, the moon looks smaller. Okay, it's the same moon. In fact, when the moon is on the horizon, because it's coming through the curved atmosphere of the Earth, that refracts the image And it actually makes the image on your retina smaller when the moon is on the horizon than when it's overhead. Yet the moon on the horizon appears bigger. It's an illusion that comes from a misperception of distance. When the moon is on the horizon, you have all the things between you and the moon that you see. So you see houses and trees and perhaps mountains. And that effectively makes the visual system think the moon's further away when there's nothing between you and the moon, when it's directly overhead. The visual system thinks it's closer because there's no intervening objects. But now here's the paradox. The actual experience, when you ask people about it, they said the moon on the horizon is bigger and further and closer. The moon overhead is smaller and further away. So there's both a conscious and unconscious component of that illusion. Okay, what I want to do now is give you a sort of standard psychology task to do. On each slide, there are going to appear two symbols, some of them familiar, some of them not. And I want you to say to yourself, you don't have to say out loud, but to say to yourself whether they are the same or different. And notice how long it takes you to make that judgment. So this is conceptually a reaction time experiment, asking how long does it take to do a particular task. So here's the first two. Oops. Next two. Next two. Next two. Okay. Presume that gave you it's easier. It's easier when things are familiar and close together. If they are unfamiliar and close together, it's still pretty. When the physical match is not there, but it's a conceptual match or mismatch. There's a conceptual mismatch, but notice it's just rotated. Those are exactly the same shape. One is rotated 180 degrees with respect to the other. Here's unfamiliar. Here's a conceptual match. A capital K and a small k, so they're not physically the same, but they're the same name. It takes us longer to respond to a name match than a physical match. And then finally, unfamiliar and far apart is the hardest. Relate this to real life experience. If you're in a country where the writing system is different than the one you're used to, I experienced this in Japan. So I knew the street I wanted, written in Japanese characters. But to actually find it, I could go to each street corner and stand back and forth between where I had the name of the street written. Because I'm not familiar with Japanese character writing system. And so I end up there like this. Whereas when I look for an unfamiliar street in San Jose, I get the street name, I can hold that in memory and look at each street corner as I go past until I find the one that matches the name I have in memory. Part of being able to hold things in memory is having them be familiar. Okay. Going on with how our system works. When babies are born, they can hear the speech sounds of all the languages human beings speak. So there's a phonological system that we use in English, one that's fairly similar in Spanish, Not identical, but fairly similar. But depending on what language you're trying to learn, some of them involve speech sounds that are not ones we use in English. Those are very hard languages to learn to pronounce and to understand. I remember in my French class in high school, one of the techniques the teacher used for instruction was to say something and have us repeat it. And he would say something, and I would repeat it, thinking I was repeating it exactly the same. And he would say, no, and he would say what I said, and then he would say, instead, say what he said at the beginning. And initially, they sounded exactly the same. I couldn't hear the distinction that he could hear. Learning language for babies is in part learning the language system of the language they're exposed to, and learning to ignore other potential differences in sound. So babies are born about the 3rd month, they start to babble. By the 6th month of life, their babbling starts to approximate the speech sounds of the language they've been hearing. They start to sound like they're babbling. If they're in the US, they start to sound like they're babbling in English. If they're in Mexico, they start to sound like they're babbling in Spanish, and so on. There's an exception. Babies who are deaf don't start to babble like the speech that is in the environment around them. Why don't they? Because they don't hear it. So they are not learning to change how they produce speech sounds to sound like the sounds they're hearing. With respect to development, our nervous system seems to be designed to learn the speech sounds of our language early in life. So if you learn multiple languages before you go off to school, you're likely to be able to speak all of them without an accent. If, like me, you learn 2nd and 3rd languages after about age 10, without a great deal of effort, I will always have a strong accent in other languages. The accent of somebody who grew up speaking English. So there is what's called a sensitive period, a time when the nervous system is set up to learn the speech sounds of language. So it's easy to learn them early, and it gets harder later in life. There are a variety of things like that. So now let me talk about not a deaf baby, but a blind baby. Some babies, unfortunately, are born blind. Our nervous system is set up with certain areas of the brain predisposed to process visual information, other areas of the brain predisposed to process auditory information. Okay? You can use both visual and auditory information to detect location. So let me talk about location information initially. So if a baby is blind, what we find is they become better able to detect location with auditory information, and they become better in part because the part of the brain that was predisposed to do visual location gets recruited by the auditory system. So even though the predisposition, it's sort of like the wiring, is just vaguely laid out to hook that part of the brain up to visual processing of location, since it's not getting any visual input, it gets used by other parts of our cognitive system, and in this case, stays specialized for location, but it's used for auditory location. Okay. There are a variety of things that showed there are sensitive periods in developing these connections of the visual system to the processing of visual information. So if a baby is born with cataracts, if you correct the cataracts, everybody know what cataracts are? These are things in your cornea that don't allow light to pass. So they functionally give you a blurry image. If you correct the cataracts early, the baby will develop normal acuity, that is, clarity of vision. If you leave the cataracts there a long time, then when you correct it, they don't fully develop acute vision. Many adults get cataracts in old age, so now the acuity is already there. They can have the cataracts for a while and then have them removed, and they go back to normal 20/20 vision. Okay? So it's as if the nervous system is set up to rewire based on experience, and that plasticity in the nervous system declines over time. There's another example. Some babies are born with their eyes misaligned. I had a teacher in 7th grade, and it was always complicated because he had one eye pointing this way and one eye pointing this way. So when he asked us a question, we didn't know who he was asking the question of. We have surgeries that involve going in and cutting the muscle fibers and either attaching them in a different place or shortening them in order to get the eyes to realign. Having two eyes pointed in the same direction is important for binocular vision. Okay? If you cover up one eye, actually everybody do this and look around the room. Cover up one eye. You can still see depth, but it somehow is not as persuasive as when you're looking at the world with two eyes. Okay? If we correct the alignment of babies' eyes by 1 year of age, they will develop normal binocular vision. There's cells in the visual cortex that take input from the two eyes to compute depth. But if we wait until later, which used to be common because it's hard to do surgery on really young babies, and it's also a concern to do anesthesia with really young babies because they have a hard time processing it out of their system. So initially people waited till about 4 or 5. Well, it had a nice cosmetic effect. The eyes ended up pointing in the same direction, but it wasn't functional. The eyes were not giving normal binocular vision. So if you look at one of those magic pictures where the pattern of colors, when you stare at it long enough, pretty soon you see an object in 3 dimensions. People without binocular vision can't see those pictures. I want to do one demonstration here that you in fact will do in your individual sections. So look at the top set of green lines. Imagine your task is to find a horizontal green line. Notice it's very easy to see it. Now look down in the lower section. Find the horizontal green line. It's a harder task because you have to pay attention to 2 features. Our attentional system can process lots of information if we only have to pay attention to 1 feature. In the case in the upper section there, only have to pay attention to orientation. But to find the horizontal green line in the lower section, you have to pay attention to both color and orientation. Similar example here. Now look at these 2 and see which is more difficult. Then you're going to find the green line. If your experience is the same as mine, they're about equally easy. It doesn't matter that they're more on the right than the left. How about here? When you can do it on a single feature, you can search in parallel. When you have to pay attention to two things, you have to look serially. And so it takes longer the more horizontal and vertical lines there are, if they're also the two colors. How many of you are good multiprocessors? Okay. Most of the research on multiprocessing shows that you're fast, but you don't process as well as if you focused on a single thing. There are a few exceptions, a few people who've been found to really be able to process more than one thing at once. What multiprocessing means for most of us is that we're really good at switching back and forth and doing sort of okay on each task. So now let me ask you a question. Where is the sun when the full moon rises? Now I want to put this in context. We don't always see the full moon rise, but a bunch of you raised your hands when I asked about it before. How many moon rises are there in a year, approximately? It's full moon rises.
21?
Turns out it's closer to 13, but not. Lunar calendars don't quite work with 365 and a quarter day a year. But so between 12 and 13 times a year, times however old you are, those are the number of opportunities you had to learn where the sun is when the full moon rises. That's a lot of repetitions of information. So you all know, right? Because you've been taught 13 times a year for 18 or 20 years. So where is the sun when the full moon rises? How could it be that you've been exposed to this all this time through your history and you don't know? Well, let me show you the geometry. For the moon to be full, the sunlight has to reflect off the moon. So it has to be with us in the middle and 180 degrees apart. So whenever the full moon is just rising, the sun is just setting. Okay? This is an example of something that you could have learned, but you never stopped to think about it. And so you didn't learn it. I predict, having done just a very little demonstration here, getting you to explicitly think about what is the geometry that makes it such that when the full moon rises, the sun is setting, that if I had an opportunity to ask you 10 years from now, you would remember it. It requires focusing attention on it and trying to figure out, okay, what's going on here? And it's not very complicated. Any of you could have understood it if you were fascinated by astronomy. You would have learned it sometime earlier, but those of you who are not, presumably don't. I want to talk about a memory example that I did in an introductory psychology class, because it shows you another thing that influences what we remember. So I went into my class, first day of the semester, and I had arranged with a member of the football team who was African American and about 80 pounds heavier and about 10 inches taller than me. And so at the beginning of class, right as I'm beginning to lecture, he comes in and he says, Dr. Cooper, I want to talk to you about my grade from last semester. And I say, well, this really isn't a good time. He said, I really need to talk to you about it. And so I shove him away. He looks and walks over to me again. He says, I need to talk about it now. So I reach into my pocket and pull out a knife. Now, it was a knife from the theater department. It was not a real knife, but it looked like a real knife. He knocked it out of my hand and went quickly out of the room. And I said to the class, I'm going to go get the police. I want you to write down exactly what just happened. Does everybody see the setup here? Well, then we collected what people wrote. Well, if you believe the written testimony of eyewitnesses right after this event happened, he pushed me. I was surprised. He pulled a knife out. I knocked it out of his hand, and then he left the room. Okay. I don't think that people thought they were lying. In fact, when I told people what had happened, there was a woman in the class who insisted that I wasn't telling the truth, that what she had written down was correct. What our preconceptions are. How often do little college professors go around pushing big football players? That's not something we expect. How often do little professors pull knives out of their pocket and threaten students? I bet that's never happened to any of you. Part of what influences memory is expectation. And they had expectations of the roles we would be serving here, and that distorted their memory. Incidentally, given the woman who wouldn't believe me afterwards, the next time I did this demonstration, I did it like we're doing this class with a video camera, so that I could then replay what actually happened compared to what people thought happened. And we'll pick up there with memory next time. Have a good afternoon.